All right, let's dive in. In this explainer, we're going to trace the line from ancient secret codes all the way to the super complex digital systems that pretty much run our world today. We're going to break down the fundamentals of digital security. Let's get started. Think about it. It's a classic problem, right? How do you communicate securely when you know anyone could be listening in? You know that one single question? That is literally the reason the entire field of cryptography exists. It's all about protecting our information. So first up, we've got to tackle the very foundation. How do we actually keep secrets safe? This is the core problem, the big question that every single security system, from your banking app to top secret military communications, is built to solve. And the toolkit we use to do this is called cryptography. It's a really simple but incredibly powerful idea. You take your normal readable message, we call that plain text, and you use a math algorithm and a secret key to scramble it into something completely unreadable. That scrambled mess, that's called ciphertext, and the only way to unscramble it is if you have the correct key. Okay, so once you decide you're gonna use a key, you hit your first big fork in the road. Should you use just one key for everything, or should you use two? Believe me, this decision changes everything. So on one side, you've got symmetric cryptography. The easiest way to think about this is like a house key. Everyone in the family has the exact same key to lock and unlock the front door. It's fast, it's simple. But on the other side, you have asymmetric cryptography. This is more like a mailbox. See, anyone can drop a letter into the public slot, that's your public key, but only you have the private key to actually open the box and read the mail. The big problem with the house key method is how do you safely get everyone a copy of that key to begin with? The mailbox method, it solves that problem beautifully. And that's the tech that powers that little padlock icon you see in your web browser every day. And this is where that key sharing problem just gets wild. Look at this. If just 10 people want to talk to each other securely using that one key method, they need to manage 45 different secret keys. Now imagine a company with thousands of employees. It's just impossible, right? This is exactly why asymmetric, that two-key cryptography, was absolutely essential for the internet to grow to what it is today. So we've got the tools, we have the keys, but what are we actually trying to do here? What's the point of all this scrambling and unscrambling? Let's take a look at the why of the game. It turns out there are 5 main goals, or you could call them the 5 pillars, that hold up our entire digital security structure. Think of these as the fundamental promises that any secure system has to make. It's about so much more than just keeping secrets. It's about creating real trust in a system. So each of these pillars does a different, super important job. Confidentiality is the classic one, keeping it secret. Integrity makes sure that the message wasn't messed with on its way to you. Authentication proves you are who you say you are, kind of like showing your ID. Obfuscation makes data just plain gibberish to anyone who's not supposed to see it. And finally, non-repudiation, that gives you undeniable proof of who sent what, kind of like a legally binding digital signature. Okay, enough with the theory, let's move into practice. How do we take all these goals and actually use them to build secure systems? Well, we do it by building a kind of digital fortress. And it all starts with a process that acts like a gatekeeper. First, you show up and say who you are. That's identification. Then you prove it, maybe with a password or your fingerprint. That's authentication. Next, the system checks its list to see if you're actually allowed inside. That's authorization. And finally, it keeps a log of what you did. We call that accounting. Seriously, every secure login you have ever done follows this exact framework. But, a single gate is never enough. The strongest security philosophy out there is called defense in depth. The idea is really simple. Build layers of security. That way, if an attacker somehow gets past one layer, there's another one waiting right behind it. The first layer is usually the technical one. This is the technology itself. You've got firewalls acting like the castle walls, encryption scrambling all the data, and systems that are constantly on the lookout for intruders. The next layer is physical, and this is a crucial reminder that digital security isn't just digital. You have to protect the actual computers and servers with real-world stuff, like locks, fences, and security guards. I mean, think about it. A firewall isn't going to stop someone who can just walk up and unplug the server, right? And the final layer is managerial. And honestly, this is all about people and processes. It's the security policies that everyone has to follow, the proper procedures for making changes, and, this is a big one, training employees to spot threats. This layer often turns out to be the most important one of all. But here's the thing about a fortress. It's never really finished. It has to be constantly maintained, repaired, and updated to deal with all the new threats that are always popping up. Security isn't a one-and-done project. It's a life cycle. The U.S. National Institute of Standards and Technology, you'll hear them called NIST, they define this life cycle in 5 stages. You start by identifying a need, then you build or buy the solution, you implement it, you operate it, and, this part is key, you have a plan to securely retire it when it's old and no longer safe. This table is a perfect example of that sunset phase in action. The original data encryption standard, or DES, was the absolute king back in its day, but with only a 56-bit key, it's now considered completely broken. Its replacement, 3DES, was better, but now it's being phased out. The current champ is AES, with much, much longer keys, which makes it secure against modern attacks. It just goes to show, what's secure today might be totally insecure tomorrow. And this brings us right to the future of security. Because this whole idea of a fortress, a secure inside and an insecure outside, that entire concept is starting to just vanish. It's being replaced by a radical new philosophy. And that philosophy is called zero trust. The core principle is exactly what it sounds like. Never trust, always verify. It just assumes that threats could be lurking anywhere, even inside your own network. There is no more trusted inside. Every single request for access has to be strictly verified, every single time, no exceptions. So in practice, what does that actually look like? Well, it means giving users and devices the absolute minimum level of access they need to do their job, and nothing more. The system is designed to separate the brain that makes the security decisions from the gates that actually grant the access. And this allows for way more dynamic and fine-tuned control over who can access what and when. This quote just says it all, doesn't it? The old model was all about building bigger and better walls. The new model assumes the walls have already been breached and forces you to act accordingly. And that leaves us with a final thought. From the password on your phone to the network at your office, all of our security is built on a series of assumptions about what and who can be trusted. So the question is, are those assumptions still safe?